Howdy, I'd like to talk about potentials and fields. So potentials and fields, they're two different things that you get with electric fields, right, with electric charges. So the electric field is a vector field at all points in space that tells you what kind of force you'll have on a charged object if you put that charged object there. So if you take everything in the world that exists, except for the thing that you care about, that's going to create this field, and then and tell you when you put the thing that you care about down, what's going to happen to it. And potentials are very much like that, except for rather than talking about the force related to the charge of an object, it's going to be the energy. So it's basically related to the potential energy that you're going to put out there. It's also a field. It's a scalar field. So the electric field is a vector field. At every point in space, there's a vector. The potential is the potential field is a scalar field, and that means that there's just a number assigned to every point that is basically related. Both of these are related to the configuration of charged particles in space that are around that can affect your system, which basically means everything in the world. But fortunately, most things in the world have such small effects that you don't really matter, and they don't really matter, so you can ignore them. We've seen a little bit of the connection between these things as an accident, right? Because I set up the same problem to work in class in two different situations. One with the field, where I used the field to find the acceleration, I used the field to find the force, then the force to find the acceleration, and then I was able to use kinematics to find a relationship between an initial velocity in a problem and the electric field. Next, I was able to. Next, I looked at the potential, and I took the potential, found the potential energy of my particle, and was able to use conservation of energy to find a similar relationship between the potential difference between two places and the velocity at the final velocity. And when I was able to do that, I was basically able to show you how potentials and fields interact with each other, or how they're related to each other. They don't interact with each other because they're both parts of the same idea. All right, just the same way that the potential energy and the force are parts of the same idea. The potential and the field, the potential and the electric field, are parts of the same idea. So we discovered that accidentally. If my doing something on purpose is accidentally. And then we were able to go off and do things. So that's what I want to talk about today, but first I'd like to go with an overview of the things that we've seen already and see where we can go from there. All right? So first off, I've got the overview about where we are in the class. So you can see that we're on that fifth lecture there, the potential field connection. Again, we're going to talk about how the potential relates to the electric field, and how the potential can be used with the work energy theorem and things like that for conservation of energy, so forth and so on. This is all something this is something we can do because we've done all this work with the charges, right? And then the forces between charges with Coulomb's law, with how the fields from charged objects propagate and what sort of things they do to other objects, with how a field turns into a force, which is just it scales with the charge. And we've also looked at just the electric potential and how that relates to the potential energy. So we'll be able to do all these other things now that we have these tools. After we're done with what we've done today, we should be ready to start talking about the electric current. Then we can talk about circuits and electronics and things like that. And after we have a good idea about what happens with electric currents, we'll be able to talk about magnetism and how magnetism works and why there are magnets, how magnets interact with each other, and so forth and so on. And that'll give us the idea of a magnetic field, which also exists in all points in space concurrently with the electric field, and they're actually connected. We'll talk about that connection eventually, how a changing magnetic field or a changing electric field can do something to the other one. And after we're done with all of that, we'll have figured out how to do these electromagnetic waves things, they'll bring us into this concept of optics, of wave optics, but we'll go through all of optics, from ray optics to wave properties, and finally we'll go down to photons and atoms and quantum mechanical ideas that deal with light. So that's our plan. Let's see where we are right now. So right now we've looked at the basics of electricity, right, of electrostatics. Like charges repel, unlike charges attract. So if you have a source charge here, and our electric, we're looking at our electric field at this point. If these are both the same charge, this thing will point, the electric field will point in the opposite direction. The force will push off in the direction opposite of them. If these things have have unlike charges, if this is negative and that's positive, or vice versa, you have to reverse this arrow, and this is going to be pulled towards the source rather than pushed away from it. So that's what that little green symbol here is, the R with the little hat on it. The rest of this is Coulomb's law, right? That the force is proportional to both the source charge and the charge on the particle. We talked about that. That's part of Newton's third law. Whatever happens to one has to happen to the other, basically, or at least the forces have to be the same. They could have different masses, and so they'd have different accelerations in the opposite direction. And it has to be the opposite direction again because of Newton's third law, right? So if we reverse this, put the source over here and the electric charge over here, R would over here would be in the opposite direction. And this is quadratic in the distance between them. We had to go all the way back to Coulomb and his experiment to figure out the R squared thing. We weren't able to do that just logically like we were able to figure out the Q and QE bit. We really did have to look at what happened, because there are other forces that could do similar things with different distance dependence, separation dependence. The electric field was this. So it's basically a something that exists at all points in space. So any particular source, if we keep the source and get rid of the object we care about, then we have that field. So that field exists everywhere because we've gotten rid of the thing that we cared about, the actual object we care about. So we just take the force at a particular place with an object and divide that through. That's the force at a point, or the electric field at a point. The point, or at the object's location, that's the point. And then we have that, but this thing's defined everywhere. So if you look at this particular case here, you can see that I have my source particle here, and all of these little arrows are part of the electric field. At any point, I could have drawn an arrow. I just got tired of drawing little arrows that showed the electric field. And you can see that this is a positive charge because the arrows are pointing away from it. And you can also see that the arrows are getting smaller as they get farther and farther away from the base object. But these arrows are everywhere. So that's the electric field, but the electric force is between two objects, always between two objects. Between every pair of objects, there's an electric force, even if it happens to be zero because one of them is not charged. One of them is neutral. And you see that if I take this object and I put another charged object over here, the force on this charged object, assuming it has the same charge, it's also positively charged, is going to be in the same direction as the field. It's going to be away from this guy, and this guy is going to feel the same amount of force in the other direction. Newton's third law again. The magnitude of this arrow is going to be proportional to the magnitude of this arrow. So here this has maybe this size, but if I go farther out, this is going to get smaller. It's because it's really just whatever the electric field is times the charge of this object, of this second object. So that's basically it. As these things separate, since there's a force on them, as these separate, that force is going to get smaller and smaller and smaller and smaller. And that's more or less what you need to know about the field. Now, that field is related to the potential in this way. The potential, like I said, is also a field. Now, in this case, it's just a number. These equipotentials, these lines that I've drawn here, they just tell you where the object has this, whatever this size is, or whatever this voltage is, this value of the potential. So it's 2 volts here, 4 volts here, 6 volts here. They're supposed to, when you draw them, they're supposed to have equal spacing. Spacing. That should not have been 8. That was just me having a brain fart while I was doing this. I went 2, 4, 8 instead of 2, 4, 6. So the potential is still a field. It's a field because it's got a value at each one of these points. It's 2 volts here. It's 4 volts here. The potential has about 3 volts in here somewhere. So somewhere in between here it's 3 volts. Somewhere out here it's 1 volt. Somewhere in here it might get to 8 volts. I don't know. I just stopped drawing these things. So probably it will. And basically, when you get to that object, you're going to stop calculating the potential, because what's happening inside the charge object is going to depend explicitly on how it is charged. So it's going to have a different potential on the inside and a different field on the inside based upon what the charge distribution is. So it'll have a different charge distribution or a different potential if it has a surface charge like a metal than it would have if it had a uniform charge, as if it were a uniformly charged insulator, as if it had a volume charge. Okay, so there we go. So let's talk a little more about the potential, because that's the last thing we actually talked about. It's a point at all point in, it's at all point in space. All points in space you have this potential. It's proportional to the potential energy, like I've got down here. The potential energy on an object is proportional to the charge of that object times the potential at that particular point. So that's the object position. This is not multiplying by V. This is the potential at X. Okay. So that's how to read that equation. Let's see. The electric field is basically the slope, how much that electric potential is changing. We'll talk more about that very, very soon. If I had two different plates here that were both neutral, or even if they had both had the same charge, there'd be no potential difference between them. But when I start moving these charges, so if I've moved some charges up here and charged up these two plates, one at minus Q and one plus Q, so they have a difference of 2Q, that's basically going to be the same as putting a battery on two plates and having a potential delta V. This battery pull out the positive charge and push it up down here onto the positive plate. So basically, no matter how I've gotten this difference in charge density, that's the same as putting this battery on and using the battery to pull the positive charges around, or basically pull the negative charges. So every time I bring a positive charge up here, a negative charge comes down here. I've got these arrows here showing where I flip them, but they have to flip by going around through the battery. We have this equation for the electrostatic potential for a point charge, just like we had the same equation for the electric field from a point charge. If we have lots of charges, we just add up all of the potentials from each of the sources, and that's going to give us the potential at a particular point. But we have to have the we have to include all the contributions from everything. And then we have this fluid analogy. Basically, what I'm saying with the fluid analogy is that the potential acts on charged particles the same way that the height is going to act on a massive particle. So if you had a potential, if you took a potential, or potential energy basically, but a potential, and you graphed it out, then you had a positive charge and you had a negative, and you had something at the bottom. If you had a low number over there, that's where everything would want to go. Just like if you had a funny shaped bowl that had little dips in it, and you poured water in there, the dips would fill up, right? And then the little peaks would stay above the water level, sort of like little islands in the water. So the same sort of thing's going to happen with the potential. Everything's going to want to go down to the lowest point of the potential, or if it's a negatively charged particle, it's going to want to go up to the top highest point in the potential. We'll talk a lot more about that later. So that's sort of where we are in the class right now. That's a sum total of our current knowledge. I'd like to go ahead and let you think about that, and then you can come and get ready. This is going to, because we're about ready for our first question, right? And we're going to do the question. We're going to introduce some ideas after we've talked about sort of the concepts behind that question and so forth and so on. So just think about this a little bit, and then possibly pause this, and then we'll go on to the next video. All right, well, thanks for listening, and I'll talk to you soon. Bye now.